Hi, in today's video we're going to be talking about graphing linear inequalities. If you are new to my channel, go ahead and click on the subscribe button so you have access to more Algebra 1 videos. Before we begin, I strongly recommend you have paper and pencil out so you can work out some of these examples and take notes with me. Alright, let's begin. Graphing a linear inequality is going to be very similar to graphing a linear equation. Throughout the year we've discussed how to graph a linear inequality by looking at the slope and the y-intercept, right? If you can identify the slope as 1/2 and the y-intercept as -1, you would first start by going to the y-intercept or the y-axis at -1 and then following the slope. The rise over run is up 1 over 2. That's what that slope represents. So you would plot your second point right here, and then you would draw your line connecting these 2 points. Now, if you notice here on the other side, we have the linear inequality version of this function. They're both going to be very similar because notice how they both have the same slope. 1/2 is the same, and -1 is the y-intercept. The thing that changes is that now, instead of looking at a y equals, it'll now be a greater than symbol, or any one of these. So we have different possibilities for inequalities. An inequality is just a symbol that represents greater than or less than to compare quantities. So the major difference is going to be that now, instead of seeing an equal symbol on an equation, you're going to be seeing an inequality symbol instead. They both are going to graph the same y-intercept, same slope, but there will be a change as we start reading the less than symbol, the less than or equal to symbol, the greater than symbol, and the greater than or equal to symbol. You've seen these symbols before in middle school when you're talking about comparing two quantities, like 3 is less than 5, 7 is greater than 2, right? But now we're going to be using these symbols in an actual equation setting. So we'll do some examples, and hopefully by the end of this video, you'll get a really good grasp of what we're doing. Before we begin graphing, a thing that we need to understand are the subtle differences between these inequality symbols. For example, here we have these two symbols that are very similar. The biggest difference is that this one is just greater than, and this one has an equal symbol underneath. So this one reads greater than 1/2x minus 3, while this one reads y is greater than or equal to 1/2x minus 3. When we're going to graph these functions, there are two things we want to pay attention to. Does it have an equal symbol underneath? Okay? If it does not have an equal symbol, whether it's greater than or less than, we're going to be using this, we're going to represent it with a dotted line. And if it has an equal symbol underneath, whether it's less than or equal to or greater than or equal to, we're going to represent it with a solid line. Now, these symbols mean something. Greater than means something, and greater than or equal to means something. So if you're dealing with a less than or equal to symbol, less than means that you're going to be shading below the line that you graph. Below the line. Or under. And then on the other hand, if you're looking at greater than or equal to, we're thinking of more than that amount. So we're going to be shading above the line that we draw. So first you have to decide, will we be drawing a dotted line or a solid line? And then you're going to have to decide, do I shade up below the line or above the line? All right, let's get to it. Let's try some examples. So here we have the equation, or the inequality, y is greater than x plus 3. I first want to look at what kind of line am I going to be dealing with? Dotted or solid? Well, there's no equal symbol, so I know that I'm going to be dealing with a dotted line. Now the shading. This symbol represents greater than. One way to remember that I like to use is the L. If you use your left hand and try to make the L, right, it will look very much like the symbol, except that the L is a little bit more crooked or slanted to the right. So this represents less than, and then the other symbol will represent your greater than. I like to also think of this as like the Lexus symbol. If you're into cars, that looks like your Lexus logo, and then the other one would not be. So for shading, here we're dealing with greater than symbol, which means we're going to be shading above the line. Now that we know these two major top parts of the graph, let's graph it. Let's identify the slope and the y-intercept. The slope here is right in front of x, which in this case is 1 over 1. And the y-intercept is your b, right? We have mx plus b. So we have a positive 3. So I start at the y-intercept. I'm going to graph this in black. We start at the y-intercept. The slope is 1 over 1. So I go up 1 over 1, up 1 over 1. And as I start connecting these lines or these dots, I want to connect them like this. Now, the biggest thing, right, as I said earlier, is that what type of line are we dealing with? A dotted line. So I need to make sure that this line that I have here is actually dotted instead of solid. So it's still going to have the same slope, the same y-intercept, but now the line is going to be dotted because we're dealing with a greater than symbol versus a greater than or equal to symbol. Now, we said we were going to be shading above the line. This is what it's going to look like. Any point above the line will be part of the solution. So we shade above. And anything in the shaded region will count as part of the solution, except anything on the line because the line is dotted. Since the line is dotted, it will not count. It'll have to be anything greater than that amount. Let's try another one. So here, before I identify the type of line, the shading, slope, and y-intercept, I need to make sure that this function is written in the slope-intercept form. I need to make sure that it is in y equals mx plus b. Because in this notation is when I will be able to find the slope and the y-intercept. And right now it's in standard form. Now I can graph it in standard form, but I want to make sure that I convert it to y equals because the symbol will make a big difference in how we shade from when it's in y equals. So let's do this. Let's start with this problem and let's solve for y. So we write the problem as is and we solve for y, which means we isolate the variable. We're going to move the 2x to the other side. Since it's a positive 2x, we're going to do the opposite. We have y greater than or equal to mx plus b, which is negative 2x minus 4. Now I can identify the slope and the y-intercept. So my slope is going to be negative 2, and the y-intercept is negative 4. And I got it from this function that's in y, and y equals mx plus b notation. So let's go to the line. What kind of line am I dealing with? Well, because there's an equal symbol here, I'm going to be dealing with a solid line. And because it is a greater than or equal to, I'm going to be shading above. So we go to negative 4. And the slope is negative 2. So I'm going to go down 2 over 1, down 2 over 1. and I can continue in the opposite direction. As I connect these points, I'm going to connect them with a solid line instead of a dotted line as before. Again, solid line because we have the equal symbol in there. Now, we're supposed to shade above this line. So anything above the line will be part of our solution. So anything in the blue section that you see here will be considered part of the solution. And here in a little bit, I'll explain more of what that means, algebraically and graphically. Let's try another example. Now here I have y less than -4. If I were to write this in, the mx plus b notation, I have no slope and I have a -4, right? If I look here, I'm missing a slope, so I can put 0 for x. Now, if you want to think about this also as Hoivux, right? Here we're dealing with a horizontal line because we have a 0 slope, and we have y equals as our equation. Now, we go to -4, we go with a 0 slope, and we'll graph that in a little bit. So I'm going to identify my slope at 0, my y-intercept is -4, and let's talk about the shading and the type of line. Because this line, because it does not have an equal symbol underneath, it's going to be dealing with a dotted line. And because it's a less than symbol, we're going to be shading below. So let's graph it. The y-intercept is -4. The slope is 0, which means we're going to be dealing with a horizontal line, right? Hoi. And this line will be dotted at -4. Now, we are going to be shading below, as we mentioned before, because it was a less than symbol. So our solution set will be everything below this line. So now let's go the other direction. Let's say that I give you a graph. Can you write the linear inequality that corresponds to this? Okay, we'll do 2 examples of this, and then we'll start wrapping it up, explaining how to check a solution. So when you're writing a linear inequality, we're going to do the very, very same thing as we've done before when you're writing a linear equation. We want to find the slope and the y-intercept. The slope can be found by the graph and the y-intercept as well. The y-intercept here, I can already see it crosses the y-axis at 1. So this part is going to be 1, and then the slope, I start at 1, and I go the rise, up 1 over 1, up 1 over 1. I notice the slope is positive 1 over 1. So the slope is just 1 as well. So this equation, if it were an equation, we would be writing it in the form of y equals 1x plus 1. But since we're not dealing with equations anymore, we're dealing with inequalities, now I want to pay attention to what kind of line is it, solid or dotted, and are we shading above or below? So since we're shading above this line, I'm dealing with greater than, the greater than symbol, because we're shading above. And because we're dealing with a dotted line, I want to make sure that there's no equal symbol underneath. So it's just y is greater than 1x plus 1. That's your equation. Let's give another one a try. So I have my equation in the form of y equals mx plus b. Let's find the slope, and let's find the y-intercept. The y-intercept, I can tell it's going to be down here at -1. So I'm going to write that over here. -1 is my y-intercept. My slope starting at -1 is going to go up 2 over 1. Up 2 over 1. Right? Up 2 over 1. So my slope is 2 over 1, or just 2. As I write my equation, I have y equals 2x minus 1 as mx plus b. Now, I'm going to be deleting this equal symbol, and I want to make sure that I now use the inequality part because I'm shading the graph. Because I'm shading below the line, I'm going to be thinking about the less than symbol. But because the line is solid, I need to make sure that I account for that by putting an equal symbol underneath. The line is solid and we're shading below it, so less than or equal to 2x minus 1. And that's pretty much it. Now let's talk about how do you identify a solution and verify whether we have a solution in a linear inequality. So we're going to check to see if these 3 different points are considered part of the solution set to this inequality. I am given here the equation and I'm given here the graph. So I'm going to first check these by using the graph, and then I'm going to show you how you can also check that using the equation, just in case you're not given the graph. Okay, so 2, 5. Anything is going to be considered part of the solution set if it is part of the shaded region. If it's in the shaded region, it will be counted as part of the solution set. So I'm going to color code these. Let's start with 2, 5. I go to 2, I go to 5. The point is right here. That is 2, 5. Because it is in the shaded region, I'm going to say yes. Now, how do I verify that on the equation aspect of things? Well, if I plug in this as x and as y into my original inequality, it should be able to work. What does that mean? I have y is greater than x plus 1. I'm going to substitute the 5 for the y. And it should be greater than substituting the 2 for the x, 2 plus 1. On the right side, we have 2 plus 1, which is 3. Is 5 greater than 3? Yes. That's how I can check algebraically that this is part of the solution set. This should work in our inequality and in our graph. And every time we choose any point on this shaded region, this inequality should function. It should work. And as you can see, 5 is greater than 3. Let's try to 4, 1. I'm going to change colors here so we can color code things. 4, 1 should land in the not shaded region. So this should not work because it's not in the shaded region. Let's verify. I have the inequality y is greater than x plus 1. And I'm going to plug in. I'm going to substitute. Let me clean this up a little bit. Y is greater than x plus 1. The y value here is 1. The x value is 4. Notice how 4 plus 1 is 5. Is 1 greater than 5? Absolutely not. Another way to check that this is not a function, not a solution set for this inequality. 1 is never greater than 5. Let's try this last scenario. Put this one in green. 6, 7. Now on the graph, 6, 7 lands exactly on the dotted line. Whenever it lands on the line, we have to be careful whether the line is dotted or solid. And here's why. If I plug it into the equation that I have, or the inequality, y is greater than x plus 1, I want to plug in 7 for y and 6 for x. On the right hand side, I have 6 plus 1. So the question I want to ask myself is 7 greater than 7? can a number be greater than itself? Absolutely not. Now, this could function, or this could work if it was 7 is greater than or equal to 7, but 7 will never be greater than 7. So anything on a dotted line, if you ever have a point on a dotted line, it'll never be part of the solution set. It has to be above it for it to be greater than the line, not equal to it. So this is also not going to work. Let's give another one a try. Why don't you give this one a try yourself? Feel free to press pause at any time and try them yourself. So I'm going to check them on the graph and using the function. 2, 1. Let's start with this one as blue. 2, 1 should work. I'm going to plug it in. So into my equation I have, or my inequality is y is less than or equal to 2x plus 1. The y value is 1. The x value is 2. Now, since I have 2x, this is the same thing as saying 2 times x plus 1, or 2 times 2. So 1 should be less than or equal to 2 times 2 is 4 plus 1. So when we simplify, we have 1 is less than or equal to 5, and 1 is less than or equal to 5. Another way to check that works. Let's try 7, 2. 7, 2 should land right here. That should also work. Let's try it out. Y less than or equal to 2x plus 1. Plug in 2 for y. 2 should be less than or equal to 2 times 7 plus 1. We do parentheses first. So 2 is less than or equal to 2 times 7 is 14 plus 1. And 14 plus 1 is 15. 2 is always going to be less than or equal to 15. Check. Let's try 3, 5. Let's do this one in green. 3, 5 should land right on the line. Just like before. What happens when it lands right on the line? We have to be careful whether the line is solid or dotted. Here we have a solid scenario, so let's check out how this will also work. So we have y is less than or equal to 2x plus 1. The y is equal to 5. So I substitute 5 is less than or equal to 2 times 3 plus 1. Sorry for my handwriting here. We do parentheses first. 2 times 3 is 6. So 5 is less than or equal to 6 plus 1. And notice how we have 5 is less than or equal to 7. Which is true. On the line, if the line is solid, it'll always work out. The equal to symbol gives you the option of making sure that these two numbers can match or equal to each other. This is pretty much it, guys. We've done several things. We've talked about how to graph a linear function, a linear inequality, and then if I give you a linear inequality or a graph, can you go backwards and write the equation, and then how to check solutions. And that's pretty much it. So let's try one last example to wrap it all up and put it together. Why don't you give this one a try? Is 2, 4 in the solution set of the following inequality? You can graph it. You can check to see if it's in that point is in the shaded region. You can even plug in the point in here to see if it's true. Let's start by graphing. Or let's start by plugging things in. This represents x, represents y. So if I plug in x in here and y in here, it should be greater than 15. Or not, we'll find out. So let's do substitution. So I have 3 times x, which is 2, minus 5 times y, which is 4, greater than 15. Let's find out. 3 times 2 is 6. 5 times 4 is 20. Is that greater than 15? 6 minus 20 is negative 14. A negative number will never be greater than a positive number. So this is not a solution. Let's try this on the graph. Now I'm going to shrink this real quick just to make enough space for me to do the work by hand so I can show you how to graph it. Remember, in order to graph this, I need to make sure that my equation or my inequality is in y equals notation. So I need to get rid of, I need to get rid of this 3x to the other side. I need to make sure this is in y equals mx plus b notation. Let's change colors here. So to put it in y equals mx plus b, I'm going to first move the 3x over. Since it's positive 3x, I'm going to subtract 3x on both sides. I have negative 5y greater than negative 3x plus 15. To leave y by itself, I'm going to divide both sides by a negative. Now this happens to be a very special case. Whenever you divide by a negative, we have to make sure that we flip this sign. It's a very important rule. If you're dividing by a negative, you have to flip the sign. So the equation is actually going to be y is less than the rest of the function. Negative 3 over negative 5 changes to positive. Dividing by a negative does that. So we have positive 3/5 x. Let me clean this up a little bit. And then 15 divided by negative 5 is a negative 3. So I have my slope, I have my y-intercept. I know that the line here is going to be dotted because there's no equal symbol underneath. And because it's a less than symbol, I'm going to shade below. So, biggest thing here is when you're solving for y, if you divide by a negative, the sign's going to flip. Notice how we started with the greater than symbol and we ended with the less than symbol. So let's graph it. We have negative 3 as our y-intercept. That's down here. The slope is 3 over 5, so I'm going to go up 3. 1, 2, 3 over 5. 1, 2, 3, 4, 5. And I'm going to connect these 2 points with a dotted line because there's no less than or equal to, it's just less than. So I'm dealing with the dotted line. And because it's less than, I'm going to shade everything below the line. This will be part of my solution set. Now, if you had just started with the problems like, oh, that's greater than, I'm going to be in the top. I'm going to check 2, 4. Yeah, that point is up here. That point is clearly not in the shaded region. Now, have you not done solving for y, as we did here, you wouldn't have flipped the sign, and you could have assumed that 2, 4 was going to be greater than this line. It was going to be above the shaded region, and it might have been a solution. So it's really important that you solve for y so that you can check to see if the sign changes, and then you can also find the slope and the y-intercept. Alright guys, I hope this has helped. Click the like button if this has been useful to you. And as always, we'll calculate later.